In this video, we're going to be taking a look at section 5.3, which covers points on circles using sine and cosine. So we're going to talk about sine and cosine first. So for a point x comma y on a circle of radius r at an angle of theta, we can define two important functions as the ratios of the sides of the corresponding triangle. So let's take a look at this picture. The sine function is going to be a function of the angle. So the sine of an angle theta, I guess I've said it a couple times. This symbol right here, it looks kind of like a circle with a horizontal line through it. It's the lowercase Greek letter theta. And it's a very common letter for us to use for angles. So the sine of theta is going to be y over r. So if this is our angle theta, notice it's measured from the positive x-axis, then the sine of that angle is going to be y, which is the y value of the point, over r, which is the distance from the origin to the edge of our circle, so it's the radius. If you're familiar with SOHCAHTOA, that all still applies. We're going to talk more about that later. The cosine function, cosine of theta, is x over r. So we have this horizontal side over the radius as well. So we're going to start by finding sine and cosine. This says the point 3, 4 is on the circle of radius 5 at some angle theta. We want to find the cosine of theta and the sine of theta. So we were told that the sine of theta is equal to y over r. Well, they gave us a point, 3, 4, so that means our x value of the point is 3, the y value of our point is 4, and they told us that this has radius 5. So I just have to plug those in. Y is 4, r is 5, so our sine is 4/5. It said cosine first, finding them out of order, that's okay. So the cosine of theta, whoops, there we go, is equal to x over r, and that's going to be 3 over 5. Let's keep working with this idea. So we're going to use sine and cosine a little bit. The point P is on the unit circle. Okay, that's important because that means our radius r is equal to 1. If the y-coordinate of P is -3/5 and P is in quadrant 4, then find the x-coordinate of P. All right, so they told us the y value. The y value is -3/5. Well, let's think about what's going on here. So the y value is negative. So that means we're going down. But we know that our radius is 1. So if we think about this being on the unit circle, then our triangle is going to look something like this, where our y value has us going down 3/5, and we know we're on the unit circle, so our radius is 1. We want to find the x-coordinate. Notice that it says that we're in quadrant 4. That's why I built it this way, is so that if that's our starting side, then in quadrant 4, we're going to be moving down here into the bottom right-hand corner. And that's how we know that this is our y side, because we're going down 3/5, and this is our radius of 1. So we're trying to find the x-coordinate. Well, that's a right triangle, so we can use the Pythagorean theorem. In this case, it'll be x squared plus y squared equals r squared, just based on the triangle. So we'll have x squared plus -3/5 squared equals 1 squared. That means x squared plus 9/25 is equal to 1. If I subtract over the 9/25, then x squared is equal to 16/25. I square root both sides. Don't forget your plus or minus, and we get x is equal to plus or minus The square root of 16 is 4. The square root of 25 is 5. So x is equal to plus or minus 4/5. But remember, we're in quadrant 4. If we're in quadrant 4, that means we are down here. In that area, our x values are positive. So we want only the positive value. X is equal to 4/5. Now we can kind of use this idea to help us build a table. And here I have a table of just some really common sine and cosine values. We are going to be using these so much, it's crazy. So I have our angles listed in degrees because those are the ones you're probably familiar with. I have them listed in radians because we'll be using those fairly frequently as well. And then we have our sine values and our cosine values. So at 0, we have a sine of 0 and a cosine of 1. At 30 degrees, which is pi over 6, our sine value is 1/2. Our cosine value is square root of 3 over 2, and so on and so forth. I'm going to keep this table around because I think it's going to help me moving forward. So far we've been using a point on the unit circle, and that makes life a lot easier. But if we're looking at a circle of radius r, then that means we can use any circle. On a circle of radius r at an angle of theta, we can find the coordinates of the point x comma y at that angle using x equals r times the cosine of theta and y equals r times the sine of theta. The reason for this, remember, the cosine of theta is equal to x over r. So if we multiply the r value over, then x is equal to r times the cosine of theta. Same thing for y equals r sine of theta. Using this information, we can prove the Pythagorean identity. We're not actually going to prove that now, but know that this is one thing you need to have memorized. For any angle theta, sine squared of theta plus cosine squared of theta equals 1. So if you take the sine value and square it, and add it to the square of the cosine value, you get 1 every single time. So we're going to use that idea to find the coordinates. So it says, find the coordinates of the point on a circle of radius 5 at an angle of pi over 3. You'll notice we don't see degrees on that, so that is measured in radians. So we said that x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. Well, we know that r is 5, so I'm going to plug that in. I need to know the cosine of theta and the sine of theta. So I'm going to go back to that table, and we're looking at pi over 3. Pi over 3, so that's 60 degrees. The sine value is square root of 3 over 2. The cosine value is 1/2. So cosine is 1/2. Let's put that one in. And the sine is square root of 3 over 2. So that means our x value is 5 times 1/2, which is 5/2. The y value is 5 times the square root of 3 over 2, which is literally just 5 times the square root of 3 over 2. And we're going to leave it just like that. What's going to be kind of a theme this unit is that even though our calculators can do this, most of these answers are going to be gross, and our calculators can't always tell us that this number, if you were to type it in as a decimal, represents 5 times the square root of 3 over 2. So a lot of this is going to be working through it by hand. So just kind of practice knowing that x is r cosine theta, y is r sine of theta. Those are going to be really super important. Now you may have noticed that in that little chart I was looking at, all of our angles were between 0 and 90 degrees. But what about other quadrants? So if you take a look at this picture we have here, we have, let's start over here. We have an angle theta that goes from here to here. And we're still working with this triangle, so our point xy. Well, wait a minute. Doesn't this triangle look a lot like this triangle right here? That's interesting. Well, wait a minute. We said that x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. So since the radius is always positive, then if x is negative, cosine is negative. If x is positive, cosine is positive. If y is positive, sine is positive. If y is negative, sine is negative. So let's go through that. Let's start with sine. So sine is positive if y is positive. Y is positive up here and negative down here. For cosine, we have to rely on the sine of our x value. Well, x is positive if we move to the right, so that'll be here and here. X is negative if we move to the left. So it looks like sine and cosine are both positive in quadrant 1. Sine is positive, but cosine's negative in quadrant 2. They're both negative in quadrant 3. And sine is negative, but cosine is positive in quadrant 4. Now remember how I pointed out this kind of similarity between these two triangles? That brings us to what's called a reference angle. And this is going to be key. I need you to be able to find reference angles and use them. An angle's reference angle is the size of the smallest angle to the horizontal axis. The reference angle is always going to be between 0 and 90 degrees because no matter where you are, you're going to be able to get to the horizontal axis. So for example, if you're in quadrant 1, then your reference angle is going to be this distance here because that's how you get to the horizontal axis the fastest. If you're in quadrant 2, that's going to be coming to the negative x-axis. If you're in quadrant 3, the fastest way to get to the horizontal axis is by going backwards. And then if you're in quadrant 4, it'll be by going forwards to the positive x-axis. What's really cool about this is when it comes to reference angles, angles share the same cosine and sine values as their reference angle, except for the sines, and we're going to be able to figure those out. So something might be positive or negative, but the actual numerical value is not going to change. So we may have a full angle being from there to there, from the positive x-axis all the way around to there. But we can find the sine and cosine value based on the reference angle, and we're going to know the values of sine and cosine of that reference angle. So let's see if we can figure out what's really going on here. It says find the reference angle for 240 degrees, then find the sine of 240 degrees and the cosine of 240 degrees. So first we need to find the reference angle. So let's see where this lines up. Well, we're thinking in terms of degrees, so this is 0 degrees, 90 degrees, 180 degrees, 270 degrees. So 240 degrees is going to be somewhere down here. We said that the reference angle is the shortest distance to the x-axis. So I know it takes 240 degrees to get from the positive x-axis all the way over there. But I don't want all the way over there. I want the reference angle right here. That means I need to take away this top half. My reference angle, and I'm going to represent that with theta sub r. That way I know it's an angle, but it's the reference angle. It's the full 240 degrees, take away the first 180 degrees. That's going to say ignore the top part, I only want this last bit. And that leaves us with 60 degrees. We want to find the sine and the cosine. So let's take a look at our pretty picture, or sorry, our pretty graph. No, it's a table. Jeez. all these different graphical representations. Let's find the sine and the cosine of 60 degrees. We already found those in their table. So the sine is square root of 3 over 2. The cosine is 1/2. But remember, these values only give us the numerical values. We need the correct signs as well. So remember that we said if we're in quadrant 3, both sine and cosine are negative. And that's because both our x value and y value are negative down there. So the sine of 240 degrees is going to be the square root of 3 over 2, but negative because we're in quadrant 3. And the cosine of 240 degrees will be negative 1/2. It's the 1/2 because of the reference angle. It's negative because we're in quadrant 3. This is the unit circle. You will see this and use this so many times you will be sick of it. But it is so crazy useful, you have no idea. So if you take a look at it a little bit closer, in this unit circle, it gives you the angle measure in degrees, the angle measure in radians, and then this is a unit circle, so the radius is 1. So it gives you the x and y value of a point on that circle, keeping in mind that the radius is 1. But remember, x is equal to r times the cosine of theta. But since we are on the unit circle, r equals 1. So that means x is equal to 1 times the cosine of theta, which is the cosine of theta. So we get the cosine of theta, the sine of theta. 45 degrees is pi over 4. The sine is square root of 2 over, sorry, the cosine is square root of 2 over 2. The sine is square root of 2 over 2. 60 degrees, pi over 3. That point is 1/2 comma square root of 3 over 2. The x value, 1/2, is the cosine of this angle. Then you can look in the other quadrants. So you can see that in quadrant 2 over here, we have negative x values, but positive y values. That reflects the fact that sine is positive and cosine is negative in this quadrant. Sine and cosine are both negative in quadrant 3. And then sine is negative, but cosine is positive in quadrant 4. Keep this unit circle on hand, be able to reference it because it will be so useful. And notice that in this unit circle, it gives you the values for all of the angles, the full 360. And that's nice because then you don't always have to use your reference angles. You can use these if they're available. So we're going to use the unit circle. So I'm going to keep it on hand. It says, find the coordinates of a point on a circle with radius 6 corresponding to an angle of 5 pi over 4. So x is equal to r times the cosine of theta. Our r value, they said our radius is 6. I need to find the cosine of 5 pi over 4. 5 pi over 4 is right here. The cosine comes from the x value. So that means our cosine is negative square root of 2 over 2. So that's going to be negative 6 square root of 2 over 2. And the 6 and the 2 divide out, so I get negative 3 times the square root of 2. Our y value is given by r times the sine of theta. Our radius is 6. We need the sine of 5 pi over 4. The sine is given by the y value, which is negative square root of 2 over 2. Which is conveniently the same thing that we had last time. So we know this is going to simplify to negative 3 times the square root of 2. So when it is asking for the coordinates, we know we need an x value and a y value. We just found those. So this point is located at negative 3 square root of 2, comma negative 3 square root of 2. Now, as we're going through these, we're going to learn a little bit about how to use our calculator, but the one thing you have to be super aware of is the difference between radian and degree mode, because your calculator is going to be able to find the sine of angles and the cosine of angles, but there you have to be careful what mode you're in. So if you hit your mode button at the top here, you have radian or degrees. So if we do degrees, we can find the sine of 45 degrees, and there's that number. It happens to be the square root of 2, divided by 2. But if I want to do that in radians, I'm going to switch back to radians down here. I don't want the sine of 45 anymore. I want the sine of pi over 4. And it gives me the same value. So just keep in mind what mode your calculator is in. I will try to remind you as much as I can, but when you get to the homework, you're going to have to know whether you're working in radians or degrees.